Hello, and welcome to our IGEN 430 capstone presentation. Myself, Chris, and my teammates Armand, Jasper, and Renee make up Group 4, and we have designed and created a novel flow monitoring system called FlowMo. Today's presentation will cover the objectives and design requirements, the methods and the design of the project, focusing on major aspects such as the clamp and the load cell, the electronic components, and the housing. Following this, we will cover the experimental methods, how we tested our sensor, and our calibration techniques. Finally, we will wrap up by going over the project plan and review. The objectives that we wanted to achieve by creating FlowMo are to create a sensor that is non-intrusive, to be able to communicate this data wirelessly across all sensors, and for the sensor to be durable enough to be used both indoors and outdoors. Finally, we aim to package the product with a user interface that's intuitive. In order to create a valuable product that will be useful in industry, it's imperative to consider the users, their needs, and the constraints of the project. The users for FlowMo would be any industry that utilizes pipelines to transport fluids that they aim to contain in a safe manner. Upon further industry consultation, we have found that FlowMo would also be beneficial to wastewater management companies and steam power generation utilities. The needs that will be satisfied for the users are the following: to create a sensor that is easy to install and service, to have it detect minute leaks, and have a housing that is both durable for indoor and outdoor applications. Finally, we aim to provide a sensor that has a UI that alerts the user if there is a leak and where it is. The constraints of this project include the budget of $500, the time given to complete the project, roughly 2 terms, and the overall scope of the project. For our purpose, we wanted to design a product that serves a purpose and actually functions as intended. Unfortunately, another constraint that was not anticipated initially was a current global event, that being the COVID-19 virus, which occurred at the tail end of the project. The design requirements for FlowMo include detecting pressure changes with an accuracy of 10% of the operating pressure, to detect circumferential deflection with the use of a strain gauge and load cell, which is mechanically amplified by a sensor clamp. We want to design a sensor that has a runtime of 5 years minimum using battery power, and a supplemental charge with a solar panel estimated at 3.5 watts. The housing of this sensor will be waterproof and UV resistant, and using gaskets of 3 millimeters to create a seal between the top and the bottom. And finally, coating the housing to ensure it is both water and UV resistant. The housing itself will also be designed to accommodate for serviceable items such as the battery. The sensor data acquisition and readings will be handled by a microcontroller, and Wi-Fi modules will be used to communicate this data between sensors and the central hub. Finally, we will design this sensor to be used with an easy-to-understand UI that is optimized to alert the user of any leaks and where they are located.
Now let's look at the major design components, which are the load cell, the sensor clamp, the electronics, and the housing. As the project objective is to detect leaks in pipelines non-intrusively, based on research we found that because of hoop stress, the circumference of a pipe expands or contracts with a change in internal pressure. So we decided to use this concept to detect a leak by measuring a decrease in the circumference. In order to do this, we chose an aluminum load cell rated for 10 kgs, which has strain gauges that convert a mechanical force into an electrical signal and are typically loaded in bending. Now we designed and manufactured a clamp that goes around a 4-inch pipe and has 2 vertical arms. It is always installed in tension with the load cell in an S configuration using M4 and M5 bolts and spacers in between. When the pipe contracts, the arms relax inward, so the load cell bends and measures a change in force. The clamp was made from a 1mm stainless steel sheet cut into a 2cm strip. After the holes were drilled for the bolts, the vertical arms were bent at 66 degrees, and then an initial curve was formed with a 6-inch pipe before installation onto the 4-inch pipe. It is simple to manufacture, cost-effective, easy to install, and most importantly, it can be scaled to larger pipe diameters.
The main functions of the electrical circuit for FlowMo include measuring load cell readings, communicating the data over a wireless connection, and sustaining the device's power requirements over a long period of time. The main components of this circuit include a Node MCU microcontroller and a load cell connected to an amplifier. Capacitors are included to reduce noise in the amplified signal, and convenient control features such as main power buttons and dip switches are built in to allow the operators to easily control and adjust the behavior of the module. Additional electrical components for power management will be introduced by Jasper shortly.
To ensure a lengthy runtime, FlowMo will source power from both battery and solar power. The device will be powered by a 2500 mAh LiPo battery and recharged by a 3.5 watt solar panel. The power supply system will be regulated by a solar charger called Sunny Buddy to ensure smooth charge and discharge cycles.
There are 4 steps related to handling the data in our system. The first step is to acquire the data using a microcontroller from a calibrated load cell. The microcontroller parses this data and transmits it via a wireless connection to a Google Apps script, which filters the incoming data for relevant information and logs it in a Google Sheet. The Google Sheet acts as a central database for all FlowMo modules, but it is also the analytical brain of the system, which turns this information into knowledge by using a leak detection algorithm. Apart from carrying out all the back-end analytics, the Google Sheet also presents the information in an intuitive format to provide at-a-glance information to operators in what is called the dashboard. The dashboard provides high-level information such as maximum, minimum, and average pressures in the pipeline as measured by the FlowMo modules distributed along its length, and then also highlights if there is a leak detected or a battery level that is lower than the threshold throughout the pipeline. If the operator wants to know high-level information for a specific location, they simply have to scroll down to a more detailed view. The incoming data is sorted based on location, and each FlowMo module has a sheet to itself. The log data is then filtered by a SQL type query within Google Sheets to form another table of the previous 30 readings in reverse chronological order. These 30 readings are used to calculate a moving average, which is then compared to the most recent reading. If the percentage drop between these two numbers is more than a preset threshold value, the location is categorized as having a leak. There are also two graphs for each location, one which maps the pressure throughout the time period that FlowMo has been running at that location, and the second maps only 30 most recent readings to provide a more zoomed-in short-term view.
To increase the accessibility and convenience of the operator, the team has created a smartphone application. Using OpenS App, a free app creator, the application will allow operators to access system information in a mobile-friendly format. As you can see, the operator will have access to the overview of the system information. And if you scroll down a bit, you can also see a graph showing each location's pressure reading live at the moment. There are also other different tabs showing the live location pressure reading and the battery status. With a 2500 mAh battery, the microcontroller can run for around 30 hours. To ensure the device can run in remote locations with long duration, Deep Sleep Mode was implemented to minimize power consumption. As shown on the slides here, Deep Sleep Mode will drop the power consumption by 99.9%. The team has chosen a cycle of 590 seconds Deep Sleep Mode interval, followed by 10 seconds regular mode. It is determined this is enough time for the microcontroller to reconnect to the server, measure data, and enter Deep Sleep Mode again. Through estimations, a 2500 mAh battery will, therefore, be able to power the device by around 60 days. With a conservative estimate of 4 hours daily sunlight and 60% efficiency, the solar panel will generate 8.4 watt-hour per day and 1.2 amp-hour per day.
The last major component is the housing. It contains the sensor clamp, the electronics, and the solar panel. It is divided into two halves with total dimensions of 21 by 9.5 by 25 centimeters. It has a cutout section in the middle for the 4-inch pipe to go through. A rubber gasket between the two halves and the cutout section make the housing water resistant to protect the internal components from the environment. It was 3D printed with ABS plastic for its structural properties. The bottom half has a recess for the rubber gasket and tabs on two sides for the top half to secure into and form a water-resistant seal. The electrical circuit is positioned in the empty space on the flat surface. The electronics will be concealed by a 3D printed cover with holes for the wires to come out. The battery, however, will be stored in a pocket to the side. This modular approach was taken so that the battery is easily accessible for replacement and the electronics are not accidentally tampered by the field operator. Now the bottom half is suspended on the pipe with a Velcro strap. It has one loop for the strap on the sidewall, but the other loop on the bottom surface. This was done so that it can remain suspended on the pipe when the top is removed and doesn't interfere when the battery is replaced. And the side loop helps in easy installation with one hand. Also, only one offset strap is used to avoid redundancy and make the housing as compact as possible.
The top of the housing is designed to accommodate the long sensor clamp arms. This portion of the housing is placed on top of the pipe and clamp arms. The provided security fasteners will bolt and secure the top of the housing to the bottom. This will be a pressure fit, as both the top and the bottom have a 3mm gasket designed to compress when installed. In order to aid in waterproofing, the top of the housing has a small lip that runs along the base of this part. This lip is intended to stop any liquids from landing on the main gasket. The top of the housing also has two holes, one for the solar panel input, and the other is to mount the solar panel hardware. For the solar panel, there are two main components, the mount and the swivel. The mount that is supplied is robust and extends to fit larger solar panels if needed. The swivel allows the user to direct the angle and the position of the solar panel for maximum light exposure. Next, we will go over the experimental methods of this project. This involves the use of our testing rig and how we calibrated the sensor. The testing rig is a 4-inch diameter pipe that is sealed on both ends. This rig was designed to simulate a leak that can be controlled. It allows for the user to pressurize and depressurize as desired. The main components of the testing rig are the pressure relief valve, the pressure input, and the pressure gauge. The max pressure for this system is 46 psi, of which the team pressured it to around 30 psi for testing purposes.
A variety of long-term tests were carried out on the testing rig to confirm the correlation of the sensor readings to the gauge pressure measured by the testing rig. The average leak rate of the testing rig was calculated over all of the tests carried out, and the normalized average leak rate has been applied to each of the tests you see right now. The x-axis is the number of readings and the y-axis is the pressure. On all of these graphs, the orange data points are the gauge pressure values, or what can be called the true pressure, and the blue data points are the measured pressure values from the FlowMo sensor. The first test was a simple leak test where the testing rig was allowed to naturally leak pressure over a 12-hour period, starting at 30 psi. The second test was similar, but once the pressure in the rig had reached 0 psi, it was pumped back up to 30 to confirm that the sensor can also detect large changes. The third test was an oscillating test where the pressure was allowed to briefly reduce from 30 before it was pumped back to 30 to test the short-term response of the sensor. The last test was one where the sensor's first reading was starting at a pressure lower than 30 psi, and then the second reading was with the pressure being at 30 psi, after which it was allowed to naturally leak. Here you can see most of the components needed to complete the installation of the FlowMo module on a pipeline. Due to unforeseen circumstances, we were not able to bring all the completed components to the same location to do a complete installation for this video. However, we will demonstrate that it is easy enough to do for one person working alone. The components you see on the screen are the FlowMo circuit board, the sensor clamp, with the load cell attached as it would come out of the box, the Sunny Buddy, and the battery. The first step is to install the sensor clamp on the pipeline. To do so, simply spread the arms of the sensor clamp apart and place the clamp around the pipeline. Use two hands to gently bring the two arms together and then insert one screw into a hole of the clamp and put the spacers on the other end, between the sensor clamp and the load cell. After a few turns by hand, let go of the clamp while ensuring it is loosely held together by the screw. Repeat the previous steps for the second screw. Using a standard 4mm or 5mm hex key, start to evenly tighten both screws. Tighten until you have achieved a snug fit and do not over-tighten. Next, connect the 4-pin DIN cable from the load cell to the receptacle on the main circuit board. Once the male and female terminals are securely connected, screw on the waterproof cover. The keyed layout of this connector prevents technicians from incorrectly installing the load cell. Lastly, using the power button, turn on the circuit and use the dip switches to enable deep sleep mode on the module.
The team has been given a budget of $500 over the duration of the projects. The table below shows the budget breakdown of the project as well as the expenditure as of March 9th, 2020. The team has exceeded project budget by $50 due to the high cost and import tax of the solar panel. In conclusion, the team is able to meet the objective of the project and deliver a functioning device that can monitor pressure drop of a pipeline system. As demonstrated in this video, the team has built a pressure sensor from scratch, created the circuitry, 3D printed the device housings, and assembled different parts together. The team has prepared and tested the device way ahead of the original deadline. This diligent work has proven to be successful and rewarding, given the team is able to deliver a functioning device in the current situation. If the team has more time to work on the project as intended in the original schedule, the team would go forward to paint the housing, do a detailed final assembly, and perform more in-depth testing to ensure the device reliability and consistency. While the device can detect a leakage on the pipeline system, the device is unable to accurately measure and predict the pipeline pressure. However, it is to note that due to the project budget constraints, an $18 sensor was used for this project. With a more accurate and sophisticated sensor, the team will be able to improve the accuracy of the device to commercial grade. Finally, this is an overview of our project. Thank you for watching our video.